Alright guys, this is part 2 of our lesson about exponential functions. This is a review. In this video we will work with graphing of exponential functions and talking about things like domain, range, asymptote, end behavior, and so on. Problem number 10. You'll notice that at no time do I use my TI-30 XS multi-view. So be careful to only use a 4-function calculator. Okay, we're going to start off by just graphing the parent function, which is 3 to the x power. So for now, don't worry about the 1/2, don't worry about the plus 2. Since we're graphing the parent function, we can stick to the values -2, -1, 0, 1, and 2. So we're doing 3 to the x power, so that means that we're doing 3 to the -2 power, 3 to the -1 power, 3 to the 0 power, 3 to the 1 power, and 3 squared. Of course, 3 to the -2 power, that's 1 over 3 squared, which is 1 over 9. 3 to the -1 power is 1 over 3. Anything to the 0 power is 1. 3 to the 1 power is 3. 3 squared is 9. Alright, notice how these first two and the last two are reciprocals of each other. Alright, that'll make it easier for you if you recognize that this always happens when we follow this procedure. Alright, 3, 1/3, 9, 1/9. The middle one is always 0, 1 for the parent function. Alright, now I'm going to erase this stuff to make room. Okay, now sometimes we need a third column. And when do we need a third column? When we have an a value in front like this. So we are going to need a third column for this problem. So in the third column, that's where we multiply by the a value. So go ahead and make a third column for this problem. Alright, in the third column, we will do the a value times the y. So we'll do 1/2 times the y column. So, we're doing 1/2 times 1/9, 1/2 times 1/3, 1/2 times 1, 1/2 times 3, and 1/2 times 9. When you multiply fractions, you multiply straight across. So this will be 1 over 18. And this will be 1 over 6. Alright, 1 times anything, of course, is itself. 1 times 1/2 is 3 over 2, which is 1.5, by the way. If you need to, think of it as 3 over 1, and again, you're going straight across. Think of this as 9 over 1. Straight across gives you 9 over 2, which is 4.5 for graphing purposes. Once you have the third column, you can really disregard the middle column. Okay, forget about it. Alright, we won't be using that column anymore. So, let's graph using the third column, but let's leave it as a skeleton. Don't connect the dots. Alright, so I've got -2 is 1/18, which obviously is very, very tiny. It's basically going to be at 0 because it's so small. Then I've got -1 is 1/6. Alright, that's not much bigger, but just draw it a little bit higher. And then at 0, we're at 1/2, which is still pretty low, but it's half a square up. And then at 1, we're at 3 over 2, which is 1.5. So that will be right here, 1.5 squares up. And then at 2, we're at 9/2, which is 4.5. Okay, so here's 4.5. Alright, so those are the 5 points you should have graphed. Do not connect those dots, just leave that as a skeleton. So what we need to do now is we need to do the H and the K, or any shifting that there is. This one has an H, but no K. Oh, that's not what I wanted. Okay, this plus 2 has the effect of taking us to the left by 2. So what you want to do is take each of these 5 points and move it to the left 2. So this is going to end up here. This one is going to end up here. All right, left 2, and left 2. So these pink points are the real points. There is no vertical shift, so the asymptote is going to remain at 0. Show the asymptote as a dotted line. All right, now just draw your curve smoothly through your points, but make sure that your graph extends all the way to the edge of the graph on both ends. Don't just connect these 5 dots. Your graph should go all the way to the edge on the left and all the way to the edge here at the top. Okay, so your graph should look something like that. Carefully check to make sure that your dots are in the same positions as mine. All right, now we're supposed to answer some additional questions. All right, we need the domain, range, asymptote, and end behavior. All right, as usual, the domain is from negative infinity to positive infinity, since it goes left forever and right forever. The range is read from bottom to top, so this one goes from 0 to positive infinity. All right, notice the round parentheses on both sides. The asymptote is the x-axis, so that's y equals 0. And the end behavior is all about what's happening on the left and what's happening on the right. On the left, the graph is approaching the asymptote. So on the left, we're approaching 0. So that's why we're going to say, so as x approaches negative infinity, f of x approaches 0. On the right, as we go to the right, the graph goes up forever. So we're going to say as x approaches positive infinity, f of x approaches positive infinity. All right? So number 11, we've got this function. Again, let's start with just the parent function, which is 2 to the x power. Okay, so we're doing 2 to the x power. The parent function, we can stick with our -2, -1, 0, 1, 2. So we're talking about 2 to the -2, 2 to the -1, 2 to the 0, 2 to the 1, and 2 to the 2. All right, this is 1 over 2 squared, so this will be 1 over 4. This will be 1 over 2. Anything to the 0 power is 1. And this will be 2, and this will be 4. Again, notice how the first 2 and the last 2 are reciprocals of each other. Are we going to need a third column this time? Well, I don't see a number in front. All I see is this negative sign. But guess what? This negative sign counts as a -1. So we will need a third column. So in the third column, we will do -1 times y. So that's just going to make everything negative. So -1/4, -1/2, -1, -2, and -4. Once we do that, we will forget about the second column, and we will now graph these. So let's see, -2, -1/4 is about here. Okay, -1 is -1/2. Zero is -1. One is at -2. And 2 is at -4. So those are the 5 points. This is the skeleton. Do not connect the dots. All right, now let's see what kind of shifting we have to do. This -1 is going to send us to the right 1, and this positive 4 is going to send us up 4. So we need to go right 1, up 4. So we're going to move each one of these points right 1 and up 4. Okay, so this is where the 5 dots will be if you move them right 1 and up 4. The asymptote is at positive 4. You can tell because of the k value. So go ahead and draw your asymptote as a dotted line. Now go ahead and draw your curve through these 5 points, making sure you draw the graph all the way from the edge through the points and to the other edge of the graph. Do not stop short. Don't just connect these dots and stop. Alright, so your graph should look very much like this. Once again, the domain of this graph is going to be negative infinity to positive infinity because it goes left and right forever. The range is going to be from negative infinity to 4. It has to be read from bottom to top. So the order matters. Negative infinity to 4. Make sure you use round parentheses, not square. And let's see, so like we said, the asymptote is here at 4. So make sure you put y equals 4. And that just leaves the end behavior. As we go to the left, this graph approaches the asymptote. So as we go left, we're approaching 4. So we'll say as x approaches negative infinity, f of x approaches 4. So that's going to look like this. Now, as we go to the right, the graph goes down, down, down. So we'll say as x approaches positive infinity, f of x approaches negative infinity. All right, that's why we have this. All right, so that's the end behavior. Now, I think we were also supposed to say something about whether or not this is growth or decay. So looking back at number 10, this is exponential growth. You can see that the graph is increasing as we go from left to right. And that's really the word we've been using. We've been talking about increasing. Now, technically, exponential growth and decay, those words do not apply to graphs that are upside down like this. All right, graphs that have an a value that's negative. So in terms of growth or decay, this is neither growth nor decay. Decay is when you have a decreasing graph like this that is above the asymptote. That's exponential decay. However, we can say that this is decreasing. All right, so this graph is a decreasing graph, but you can't call it exponential decay or growth. So number 12. We want to start with the parent function, but before we can even really start with the parent function, we need to deal with the fact that I've got this negative x on there. Now, hear me carefully when I say this. As far as transformations go, this -1, you can consider it to be a reflection over the y-axis. That is a fact, okay? Reflection over the y-axis. So if we were listing transformations and there's a negative on there, you could mention, if you saw that negative sign, you could mention reflection over the y-axis. Now, as far as the way we actually graph the problem, we're not going to use that. Instead of thinking of it as a reflection over the y-axis, what have I trained you to do? Anyone? How do I handle this? I change it to 1/3, okay? So I encourage you to change the entire problem because 3 to the negative x power is the same thing as 1/3 to the positive x power. Now, doing that is the same thing as a reflection over the y-axis. But so let's just graph this new blue function, though, okay? So the parent function that we're going to be dealing with is this, 1/3 to the x power. So as we graph the parent function, we can just stick with our good old x values, -2, -1, 0, 1, and 2. Okay, so we're going to be doing 1/3 to the -2 power, 1/3 to the -1 power, 1/3 to the 0 power, 1/3 to the 1 power, and 1/3 squared. Now remember, if you have a -2 power, you're going to do the reciprocal. What's the reciprocal of 1/3? 3. So this is going to become 3 to the +2 power. So that's why that's going to be 9. When we do this next one, again, reciprocal is just going to be 3 to the 1 power. So that'll be 3. Anything to the 0 power is 1. Now, have you noticed that the first two y values and the last two are always reciprocals of each other? Have you absorbed that by now? So without even thinking about it, you know, this one's a 3, this one's going to be 1/3. If this one's a 9, guess what this one's going to be? 1/9. Have you noticed that that always happens when we do the parent function? Okay, I mean, when you look at it, it also makes sense. 1/3 squared is, in fact, 1/9. All right, any questions so far about the parent function values? Okay, all right, no questions. So I need to erase this to make space, because sometimes we need a third column. Do we need a third column on this problem? Yeah. When do we need a third column? Yeah, when we have this a value, this 2 in the front, that's when we need a third column. So let's add a third column on. Did you get a paper, sweetheart? Okay, so since we have an a value of 2, we're going to add the third column like this. Okay, and in the third column, we will do the a value times the y column. So that's going to make this 18, 6, 2, 2/3, and 2/9. Any questions about where the third column is coming from? Okay. Once we have the third column, we will disregard the middle column. And now we will graph the third column. Okay. So as I graph these, this is my skeleton. Do not connect these dots. So I'm going to do -2, 18. Okay. So that's going to be a little off the graph. Go ahead and just try to do it anyway. So -2, 18, so it's 15, 16, 17, 18. It'd be about here. All right, and then I've got -1, 6. So -1, 6. And 0, 2 would be right there. 1, 2/3. All right, it's going to be right about there. And then 2, 2/9, which is going to be right about there. Okay, so we have those 5 skeleton points which we will not connect. Any questions about that? Okay, now to get the final answer, oh, you know what? I was going to say, normally this is the point where we would do any shifting, because if there's an h and a k, but what's happening on this problem? There is no shifting, there is no h and k. So I keep saying I'm not going to connect the dots, but we actually are going to connect the dots because there's no shifting. This is it. This is the answer. All right, so just draw a curve through here, and you're done. Okay, go ahead and show your asymptote as a dotted line, though. All right, so there it is. Your graph should look very much like this right here. Okay, and now let's answer some questions. So the domain is the easy part because it seems like that never changes. It's always -infinity to +infinity for these exponential curves. Now, what do you think about the range, people? 0 to positive infinity. It has to be from bottom to top. Herbie, head up, eyes open. We have a test tomorrow. So 0 to infinity. That's my range. The asymptote. She already said it correctly. I was going to put this down and ask you why I just lost half credit. I forgot to put the y equals. So make sure you put y equals. Don't just put 0. And then the end behavior. Okay, end behavior is what's happening on the ends of this graph. So on the left side of the graph, as I go to the left, it's going up, up, up to infinity. As I go to the right, it's approaching 0. Okay, so on the left, I'm going to infinity. On the right, I'm going to 0. Okay, so, all right, so in symbols, your end behavior would look like this. As x approaches negative infinity, the function goes to positive infinity. In other words, on the left, it goes up. And then as x approaches positive infinity, the function approaches 0. In other words, on the right, it goes to 0. Okay, so that's it. In the directions, it also said something about, is this exponential growth or exponential decay, or neither? We've been more talking in terms of increasing and decreasing, so let me say that first. Is this increasing or is it decreasing? This is definitely decreasing, okay, because you see that it's going down as we go from left to right. So it's definitely decreasing. We can also say that this is exponential decay, but I just need to be clear that exponential decay and growth only applies when you're above the asymptote like this. For these graphs that are upside down, and we're not going to get into this right now, on this test tomorrow, but just going forward as we start to do word problems in the next unit. This would not be exponential growth or decay, problem number 11 here. Because it's upside down. Upside down graphs, the words growth and decay don't apply. We could still say, is this increasing or decreasing? We could say it's decreasing, but we can't call it exponential decay when it's upside down like this. Okay? What about number 10? Can I call this exponential growth? Yeah, this is exponential growth. It's right side up, so I can call it growth. Okay? It's increasing, by the way. All right, so that's it for the graphing. So I'm going to stop this video here because we're about to switch to a completely different topic. On the next video, we're going to be talking about the transformations between, you know what? Yeah, I'm going to stop the video here. On the next video, we'll talk about transformations just by looking at the equations. All right, I'll see you on the next video.